Metal manufacturing traces the journey from raw iron to steel, supplying essential materials that power heavy industries and build modern infrastructure worldwide. Modern life depends on enormous quantities of metal. From buildings and vehicles to household appliances, mobile phones, and game consoles, metals are essential materials that support both construction and manufacturing worldwide. Some of these metals are abundant, while others are rare, but all of them are costly to obtain. The true cost of metal mining is not only financial but environmental, as extracting metals from the ground causes habitat destruction, pollution, and long-term damage to plants and wildlife. Metals occur naturally as metal ores, small deposits trapped within rock. Since the Bronze Age, humans have mined these ores by digging, crushing rock, and heating it to extremely high temperatures to separate usable metal. Today, global demand has driven mining operations to an industrial scale. These massive mines require vast amounts of energy to extract ore, transport it for processing, and refine it for use, while leaving behind polluted landscapes and large volumes of toxic waste that are difficult to manage safely. To reduce these impacts, the metal recycling industry plays a critical role. Recycling recovers metals from discarded products and transforms them into new raw materials. In the UK alone, this industry contributes billions to the economy while preventing millions of tons of carbon dioxide from entering the atmosphere. Iron, steel, aluminium, copper, and even precious metals from electronic waste can be recovered efficiently. By recycling metals instead of mining new ore, energy use is reduced, emissions are dramatically lowered, and pressure on the planet's natural resources is significantly eased. Bauxite-derived alumina is delivered to the plant by rail and stored before entering the smelting stage. Inside the long pot room buildings, alumina powder is fed into sealed electrolytic cells. The powder is first dissolved in a hot, acidic chemical bath. A very large and continuous supply of electricity is then passed through carbon anodes into the mixture. Under this electrical current, oxygen is released from the alumina, while pure aluminium separates and gradually sinks to the bottom of each cell as molten metal. During electrolysis, the carbon anodes are slowly consumed by the reaction. They are therefore replaced at regular intervals with spent anode material removed and prepared for recycling. New anodes are delivered to the site and attached using a casting process. Throughout smelting, emissions such as carbon dioxide are continuously monitored and controlled to maintain safe operating conditions. Once a sufficient quantity of molten aluminium has accumulated, it is siphoned from the cells into specially designed transport vehicles. These vehicles move the metal to the casting room while it remains in liquid form. In the casting furnaces, alloying elements are added according to the required specifications of the final product. The molten aluminium is then cast into pans or larger ingots, allowing it to solidify in controlled shapes. The finished primary aluminium products are cooled, inspected, and prepared for further processing or downstream manufacturing, completing the transformation from alumina powder into usable aluminium metal. The steelmaking process begins with the preparation of raw materials. Iron ore slurry, transported through a long pipeline, first undergoes filtration to recover water. The dried ore is then fed into pelletizing discs, where it is mixed with binding agents and rolled into small spherical pellets. These pellets are heat hardened at temperatures of around 300 degrees Celsius to gain sufficient strength before being sent to the blast furnaces. At the same time, metallurgical coal is delivered by rail to the coking plant. In vertical ovens lined with refractory bricks, the coal is baked for approximately 18 hours in the absence of air. This process drives off volatile components and transforms the coal into coke, which serves as the primary fuel and reducing agent in the blast furnace. Several byproducts are generated during coking, including coke oven gas, which is later reused as fuel in other stages of steel production. Another important blast furnace feed material is sinter, a porous mass made from iron ore fines and dust generated within the steel plant itself. These fine materials are blended with lime, coke fines, and dolomite, then hardened in a continuous chain sintering oven to form strong, permeable agglomerates suitable for furnace charging. Prepared pellets, sinter, coke, limestone, and dolomite are stored in hopper facilities and charged into the blast furnace in carefully controlled proportions. The blast furnace is a tall cylindrical structure lined with refractory brick. Through the charging system at the top, raw materials are layered inside the furnace. Preheated air is blown under pressure into the bottom, igniting the coke and generating temperatures of up to 1650 degrees Celsius. In this environment, iron oxides are chemically reduced and melted, forming liquid pig iron. The molten iron collects in the graphite-lined hearth at the base of the furnace. It is periodically tapped through tap holes and directed along troughs into torpedo cars with capacities of around 200 metric tons. To reduce sulfur content, desulfurizing agents such as calcium carbide and magnesium are injected into the molten iron in a dedicated treatment station. Meanwhile, the slag formed during smelting is removed, cooled with water in slag pits, and later stored or sold as a byproduct. Pig iron is converted into steel using either the basic oxygen furnace or the electric arc furnace, EAF. In the BOF route, scrap metal is first loaded into pear-shaped converters lined with refractory brick. Molten pig iron is then added from ladles. High-purity oxygen, along with argon and nitrogen, is blown into the molten bath through lances under pressure. This refining process lasts about 45 minutes and removes excess carbon and impurities, producing liquid steel. Alloying elements are added in ladles to adjust the steel's chemical composition to the required specifications. In the electric arc furnace process, a charge consisting of scrap metal, iron briquettes, or liquid pig iron is loaded into the furnace. 3 graphite electrodes deliver high electrical energy to melt the charge. Once refining is complete, the molten steel is tapped into ladles for further processing. Steel from both routes undergoes secondary metallurgy, where temperature and chemical composition are precisely adjusted. In some cases, vacuum degassing is applied to reduce hydrogen and carbon levels for high-quality applications. The refined liquid steel is then cast into slabs using continuous casting machines. As the steel passes through water-cooled rollers, it solidifies into a slab that is cut to specified dimensions using oxygas torches. The solid slabs are reheated and processed by hot rolling to produce plates or coils. In plate rolling lines, slabs are reduced through multiple passes in reversing mills to achieve the required thickness and width. For hot strip production, slabs are progressively reduced through a series of rolling stands and then cooled and coiled. Hot-rolled coils may be shipped directly or sent for further processing. Cold rolling further reduces thickness and improves surface quality. The process begins with pickling to remove oxide scale, followed by rolling at room temperature. Annealing softens the steel, and temper rolling enhances surface finish and mechanical properties. Additional processes such as coating, structural rolling, and finishing transform the steel into final products for construction, automotive, machinery, and industrial applications. Driven by a clear vision to focus upon society and create quality, Hengyang Furnace has established itself as one of the largest and most respected induction furnace manufacturers in the world. Built on passion, integrity, and continuous innovation, the company has grown from a specialized producer into a global supplier of advanced induction melting solutions. Hengyang Furnace designs and manufactures a wide range of induction melting furnaces capable of processing steel, cast iron, aluminum, copper, brass, stainless steel, mild steel, and other engineering metals. Each furnace is engineered to deliver high thermal efficiency, stable melting performance, and precise temperature control, meeting the demanding requirements of modern foundries and metal processing plants. Inside the production facilities, advanced machining centers, automated assembly lines, and strict quality inspection systems work together to ensure consistent product excellence. Every key component, from induction coils and power supplies to refractory linings and cooling systems, is manufactured or assembled under carefully controlled conditions. This integrated production approach allows Hengyang Furnace to maintain high reliability, long service life, and superior operational safety in every unit delivered. The company places strong emphasis on research and development, continuously improving furnace design to reduce energy consumption, increase melting speed, and enhance environmental performance. By combining practical industry experience with modern electrical and metallurgical technologies, Hengyang Furnace provides solutions that support efficient, clean, and sustainable metal melting operations. Over the years, Hengyang Furnace has successfully supplied a large number of top-quality induction melting furnaces to customers across Asia, Europe, the Middle East, Africa, and the Americas. These systems are widely used in foundries, steel plants, non-ferrous metal workshops, and recycling facilities, earning trust through stable performance and dependable after-sales support. Beyond manufacturing, the company is committed to long-term partnerships, offering technical consultation, installation guidance, operator training, and maintenance services. This customer-focused approach ensures that each furnace operates at optimal efficiency throughout its service life. With a strong manufacturing foundation, global export experience, and a commitment to quality and integrity, Hengyang Furnace continues to shape the future of induction melting technology. Visitors and partners from around the world are warmly welcomed to explore the factory, witness the production process, and share in the company's pursuit of excellence. Inductotherm Corporation's factory tour showcases a manufacturing facility dedicated to induction power systems. The plant features a VIP power supply assembly area where electrical units are built and a subsystems assembly zone that brings together complex components. The automated machining center enhances efficiency, while the magnetic components assembly produces essential parts. Power transmission systems and coil manufacturing centers support reliable outputs. The Thomas H. Cook Building and COU Annex house specialized operations, including furnaces and automated systems. The Thomas H. Cook Building for large systems accommodates heavy fabrication work. Finally, an inventory and supply center ensures materials are ready when needed, reflecting excellence in industrial production. At Taruni Foundry, aluminum components are produced through a precise gravity casting process that combines advanced automation with skilled manual work. The process begins when solid aluminum ingots are loaded into a melting furnace. Inside the furnace, the aluminum is heated until it reaches a fully molten state suitable for casting. Once the aluminum has melted, operators carefully remove impurities and slag that rise to the surface of the liquid metal. This cleaning step is essential to ensure high material quality and prevent defects in the final castings. After purification, the molten aluminum is transferred to the casting area. For automated production lines, a robotic arm is used to scoop the molten aluminum and pour it accurately into permanent metal molds installed in the gravity casting machines. The use of robotics ensures consistent filling, stable process control, and improved safety. After casting, the parts are moved by a handling system and held in position while awaiting the next stage. Some components cannot be produced using fully automated machines. In these cases, experienced workers manually ladle the hot molten aluminum and carefully pour it into molds mounted on casting machines. This manual operation allows greater flexibility for complex or low-volume parts. Once solidified, the aluminum castings are stacked and set for quality inspection. An X-ray imaging system is used to detect internal defects such as porosity or cracks that are not visible from the outside. After inspection, workers grind the cast parts to remove excess material and improve surface finish. Next, density measurements and tensile strength tests are performed to evaluate the alloy's mechanical properties, including strength and ductility. Aluminum bars and selected parts are then processed in an automatic deburring grinding machine to remove sharp edges. Finally, the components undergo further inspections, resulting in high-quality aluminum castings ready for subsequent machining or assembly. Steel production begins with solid billets supplied by the melt shop and rolling mill. These billets are reheated in a rotary hearth furnace to approximately 2,200 degrees Fahrenheit, ensuring uniform temperature throughout the material. Even heating is essential for the piercing stage, where a central hole is formed to create a hollow shell. After piercing, the tube undergoes elongation to reduce wall thickness. This step uses a rotary elongation process designed for medium to heavy wall tubing, allowing precise control over outer diameter and wall dimensions. Once the desired dimensions are achieved, the tubes are cooled, using either fast or slow cooling methods. Controlled cooling develops specific mechanical properties suitable for subsequent machining and further processing. The process starts with a solid steel billet prepared specifically for hot forging. The billet is placed inside an industrial heating furnace, where it is gradually heated to a high forging temperature. Inside the furnace, the temperature is carefully controlled so that heat penetrates evenly from the surface to the core. Uniform heating is essential to prevent internal stresses and ensure smooth deformation during forging. Once the billet reaches the required temperature, it is removed from the furnace while still glowing red hot. The transfer from the furnace to the forging area is carried out quickly to minimize heat loss. Maintaining the correct temperature at this stage allows the steel to remain soft and highly formable. The first forging operation begins by applying force to the heated billet, compressing it vertically. This initial forging step shortens the billet and increases its diameter, preparing the material for further shaping. The metal begins to flow outward as its internal structure becomes more compact and refined. During the second forging stage, the billet is forged again to start forming a curved profile. Repeated blows are applied, gradually pushing the hot steel into a rounded shape. The metal flows smoothly due to the high temperature, allowing the basic dome geometry of the CNG cylinder bottom to emerge. In the third forging stage, the shape is further refined. The billet is forged repeatedly to deepen the curvature and increase thickness in critical areas. Each forging stroke improves material density and aligns the grain structure in the direction of the applied force, enhancing strength and pressure resistance. Additional forging passes are then performed to achieve uniform thickness distribution. The outer edges are shaped carefully while maintaining sufficient material at the center. This step ensures that the cylinder bottom can withstand high internal gas pressure during service. Throughout the hot forging process, the workpiece remains at an elevated temperature, allowing continuous deformation without cracking. By the end of the final forging stage, the billet has transformed into a fully formed rough bottom shape with a smooth curvature and robust structure. The forged component is now ready for the next manufacturing steps beyond hot forging. The rail clip production line is designed to manufacture high-strength fastening components used to secure rails firmly to sleepers. The process begins with high-quality spring steel bars, which are cut to precise lengths and heated in controlled furnaces to achieve optimal forming temperature. Hot forging and bending machines then shape the steel into standardized rail clip profiles such as SK, L, and E types. After forming, the clips undergo heat treatment, including quenching and tempering, to ensure excellent elasticity, fatigue resistance, and mechanical strength. Surface finishing processes remove scale and improve corrosion resistance. Finally, each rail clip is inspected for dimensional accuracy and performance before packaging, ensuring reliable operation in demanding railway environments. After being heated to the required forging temperature, the steel blanks are transferred directly to the hot forging line. At this stage, high-capacity mechanical or hydraulic presses apply controlled force to shape the softened metal. Precision dies form the bolt head and neck while maintaining uniform grain flow, which significantly improves the mechanical strength of the bolt. Depending on the design, shapes such as oval necks, diamond necks, or special profiles are produced to prevent rotation during tightening. Once the basic bolt shape is formed, excess flash material generated during forging is trimmed off. The bolts are then allowed to cool slightly to a suitable temperature for subsequent operations. After cooling, the bolts move to the threading process, where threads are created on the shank. Thread rolling is commonly used, as it displaces material rather than cutting it, resulting in stronger threads with improved fatigue resistance. In some cases, precision machining may be applied to meet strict dimensional tolerances. Following threading, surface scale and residual oxides formed during forging are removed through shot blasting or mechanical cleaning. This step ensures a clean surface and prepares the bolts for consistent heat treatment. The bolts are then carefully loaded into heat treatment furnaces, where temperature and time are precisely controlled. Heat treatment typically begins with quenching, in which the bolts are heated to a specified austenitizing temperature and then rapidly cooled using water, oil, or polymer solutions. This process increases hardness and tensile strength. After quenching, the bolts undergo tempering, where they are reheated to a lower temperature and held for a defined period. Tempering reduces internal stresses and brittleness while achieving the required balance between strength, toughness, and elasticity. After tempering, the bolts are gradually cooled to ambient temperature, completing the heat treatment process and ensuring reliable performance under heavy rail joint loads. The production of railway components begins in the steel rolling workshop, where raw steel billets are heated and passed through high-precision rolling mills. Using the 450 bearing mill auto production line, the steel is continuously shaped into components with accurate dimensions and high mechanical strength. This automated line operates with stable speed and quality control, allowing the plant to achieve an annual output of over 100,000 tons of rolled steel products. After rolling, selected materials are transferred to the rail, fishplate, and joint bar workshop. Here, steel sections are cut, punched, and machined to form fish plates that connect rail ends securely. Each joint bar is carefully processed to ensure proper alignment and load transfer on the track. In parallel, the rail clip workshop produces fastening components used to fix rails to sleepers. Advanced forming and heat treatment processes are applied to guarantee elasticity and long-term durability. Thanks to a highly efficient production system, this workshop can manufacture more than 50 million rail clips annually. The process continues in the casting workshop, which is equipped with a full automatic casting line. Molten metal is poured into molds under controlled conditions to create various railway components. Anti-dust and dust reduction facilities are installed throughout the workshop to ensure environmental protection. The casting section reaches an impressive annual output exceeding 60 million tons. Steel bars are first delivered to the cutting area, where they are fed into a cutting machine. This machine precisely cuts the long steel bars into shorter sections of equal length. Each cut segment is carefully controlled to ensure consistent size and weight, which is essential for the later forming stages. After cutting, the small steel pieces are collected and temporarily stored before heat treatment. Next, the cut steel segments are arranged in batches and loaded into a heating furnace. Inside the furnace, the steel pieces are exposed to high temperatures until they reach the required forging temperature. This heating process softens the material, making it more ductile and suitable for shaping. The furnace operates continuously to ensure uniform heating, so that each steel piece has the same temperature and material properties when removed. Once sufficiently heated, the glowing steel segments are taken out of the furnace and transferred by workers to the forging presses. Each heated steel piece is placed individually into a forging machine. Under extremely high pressure, the press compresses and reshapes the hot steel. This first forging stage begins to form the basic outline of the spring clip. After the initial shaping, the partially formed pieces are moved through a sequence of different forging presses. Each press performs a specific forming operation, gradually refining the geometry of the spring clip. With every successive forging step, the steel takes on more detailed features, bends, and curves. The repeated application of pressure improves the strength and internal structure of the metal, while bringing the spring clip closer to its final shape. Workers carefully position each piece to ensure accurate forming at every stage. When the forging process is complete, the newly formed spring clips are subjected to a cooling process. The hot components are allowed to cool down under controlled conditions. This cooling stage stabilizes the metal structure and helps the spring clips retain their shape after forging. Proper cooling is essential to prevent deformation and to prepare the clips for handling and storage. Finally, once fully cooled, the finished spring clips are gathered and stacked neatly on the workshop floor. Workers arrange the clips into organized bundles, aligning them carefully to save space and maintain order. Each bundle is securely tied to keep the spring clips together. The bound bundles are then stacked on top of one another, ready for transport or further processing, marking the completion of the spring clip manufacturing process. The PSE system is presented as a modern and fully patented solution designed specifically for reinforced steel processing workshops, where productivity, precision, and worker well-being are critical. The equipment is built around ease of use and simplified maintenance, allowing daily operations to run smoothly with minimal downtime. One of its key strengths is the optimization of raw material flow. Steel bars move logically and efficiently through each stage, reducing unnecessary handling and improving overall workshop organization. Simplified marking and layout further reduce preparation time, enabling welders to focus on high-value tasks. The system significantly improves welding performance thanks to accurate measurement and clean welding conditions, ensuring consistent quality while respecting the flatness of intermediate layers, which is essential for structural integrity. Optimized handling and a well-designed workflow reduce physical strain, while the ergonomic working position allows welders to work comfortably and safely throughout the day. PSE also offers full welder autonomy, giving operators complete control over their workstation. This autonomy contributes to the upgrading of the welder's role, transforming it into a more skilled, valued, and productive position. As a result, productivity increases in what is often the most costly section of the factory. Recognized and positively welcomed by public health organizations, the system leads to a significant reduction in musculoskeletal disorders. By improving comfort, safety, and efficiency, it also helps increase welder loyalty, making PSE a sustainable investment for both performance and people. The automobile recycling process begins when an end-of-life vehicle is delivered to the recycling yard and prepared for heavy mechanical treatment. After preliminary steps, such as fluid removal and basic dismantling, the remaining car body is transferred to the processing area. A large hydraulic crane equipped with a powerful steel grapple grips the vehicle firmly and lifts it off the ground. With careful control, the crane moves the car toward the scrap press and positions it inside the compression chamber. Once the vehicle is correctly placed, the press is activated. Massive hydraulic plates begin to close in from multiple directions, applying extremely high pressure to the car body. As the compression continues, the metal structure collapses inward. The roof, doors, frame, and remaining panels are crushed together, reducing the vehicle's volume dramatically. This pressing stage not only compacts the car, but also helps separate trapped air and loosen non-metal components that may still be attached. After the compression cycle is completed, the press slowly opens. The original shape of the automobile is no longer recognizable. What remains is a dense, rectangular block of compressed scrap metal, often referred to as a scrap bale. This compact form makes the material much easier to handle, store, and transport. The crane then returns to the press, using its grapple to clamp onto the compressed metal block. It lifts the bale out of the machine and places it neatly in a designated storage area. Here, the compressed car scrap waits for the next stage of processing, such as shredding, magnetic separation, and melting. Through this controlled compression process, large and complex vehicles are efficiently transformed into manageable scrap, supporting the reuse of metal resources in future manufacturing cycles. The recycling process begins when the damaged crawler excavator is transported to the scrapyard and positioned on a reinforced working area. Due to its large size and weight, a heavy-duty crane is used to stabilize and reposition the machine, ensuring safe and controlled handling throughout the operation. Once secured, a powerful hydraulic shear mounted on the crane moves into position. The hydraulic jaws firmly grip the excavator's structure, starting with exposed components such as the boom, arm, and bucket. These parts are torn away piece by piece, using immense cutting and crushing force. Thick steel plates, pins, and reinforced joints are ripped apart with precision, reducing the machine into manageable sections. As the process continues, the operator targets the main body, including the engine compartment, cab frame, and undercarriage. The hydraulic shear slices through hardened steel, breaking the excavator into smaller fragments. Each movement is carefully controlled to maximize efficiency while preventing uncontrolled collapse of heavy components. The dismantled metal pieces are then separated by size and type. Larger steel sections are further cut down, while smaller fragments fall directly into collection zones. These scrap materials are later transported for sorting, melting, and reuse in steel production. Through this systematic dismantling process, the obsolete excavator is completely reduced to recyclable metal, transforming heavy industrial waste into valuable raw material for future manufacturing.